Good day. The topic we are treating today is arithmetic progression and some of its properties by Opola Monsurat Olajumoke. Before the commencement of this lesson, you must have been familiar with what a sequence is and some of its terminologies and denotations. In this lesson, we explain what an arithmetic progression is, its terminologies and denotations. The nth term of an arithmetic progression is also derived and explained, and some problems are solved. Also, some properties of arithmetic progression are established and proved. By the end of this lesson, I hope you will be able to solve different problems on arithmetic progression and also apply its properties where necessary. The arithmetic progression. An arithmetic progression, also known as linear sequence, is a sequence in which the increase or decrease between any two consecutive terms, that is, the first term represented as T1 and the second term represented as T2, and the second term T2 and the third term T3, etc., is the same throughout. The increase or decrease is called the common difference, which either takes a positive or negative value. Examples of arithmetic progression with their common difference are: the first example, 5, 11, 17, 23, 29, and so on. If you are familiar with a sequence, you know this is an infinite sequence with first term as 5, that is T1 as 5. So to know if a particular sequence is an arithmetic progression, you check if the difference between the second and the first term is the same thing as the difference between the third and the second, which must also be equal to the difference between the fourth and the third. That is, in general, it must be equal to the difference between the nth and the n minus 1 term. So here, if you subtract 5 from 11, that is 11 minus 5, we give 6, which is the same thing as subtracting 17 minus 11, which will also give 6, which is the same thing as subtracting 17 from 23, which is 6, and so on. So since it has a unique difference, which is 6, therefore it is an arithmetic progression with its common difference as 6. So the second example, 3, 4 and a half, 6, 7 and a half, 9, and so on. Here, the first term is 3, the second term is 4 and a half, the third term is 6, the fourth term is 7 and a half, and the fifth term is 9. So to check for the common difference, to check if it has a unique difference, we subtract 3 from 4 and a half, we have 1 and a half. We subtract 4 and a half from 6, we have 1 and a half. 6 from 7 and a half, 1 and a half. 7 and a half from 9, and we also have 1 and a half. Since it has a unique difference, it is an arithmetic progression with its common difference as 1 and a half and the first term as 3. In an arithmetic progression, each member is called a term. The first term, that is the first number in that particular sequence, T1, that is the first term, is usually represented by A. You represent the first term, T1, by A, while the common difference, that is the unique difference between its terms, is noted by D, which is given by the formula. Is either you subtract the first term from the second term, or the second term from the third, or the n minus 1 term from the nth term, which will give you the same result. Example of arithmetic progression with their first terms and common differences are, as we have explained, this 5, 12, 19, 26, 33. This is the first term, that is the first number in the sequence. So to get the second term, to get the common difference, you subtract the first term from the second term, or the second term from the third, or the third from the fourth, or the fourth from the fifth, or the n minus 1 term from the nth term. That is 12 minus 5 will give 7, 19 minus 12 will give 7, 26 minus 19 will give 7, 33 minus 26 will also give 7. Therefore, the common difference is 7. So move to the second example, 14, 11, 8, 5. We can see that the number here is decreasing. Therefore, we know the common difference will be a negative number. Here, the first term in the sequence, that is the first number, is 14. So to get the common difference, we subtract 14 from 11, we have negative 3, or we subtract from 8 to give -3, which is also the same thing as subtracting 8 from 5 to give -3. So this is an arithmetic progression with its first term as 14 and common difference as -3. The nth term of an arithmetic progression. A sequence of an arithmetic progression can be written as A, which is the first term. The second term can be written as A plus D. The third term can be written as A plus 2D. The fourth term can be written as A plus 3D. The fifth term can be written as A plus 4D, and so on. To check if this is true, we move to the previous example we have checked. Here, the first term is 5, which is A. We said the second term can be written as A plus D. That is, you had the first and the common difference together. Here the common difference is 7. 5 plus 7 is 12. The third term can be written as A plus 2D. That is, A plus 2 multiplied by the common difference. 2 multiplied by 7 is 14, plus 5 is 19. That is the general form of an arithmetic progression. The general form of the terms in an arithmetic progression can be A, A plus D, A plus 2D, A plus 3D, A plus 4D. Here A is the first term, A plus D is the second term, which is noted as T2. A plus 2D is the third term, denoted as T3. A plus T3 is the fourth term, denoted by T4, and A plus 4D is the fifth term, denoted by T5, and so on. So from the above, that is from here, it is noted that the number of common difference that must be added to the first term in order to get the next term is 1 less than the term being sought. What they are trying to say here is that here, when you want to get the second term, you have to add only 1 common difference to the first term. We are in the second term, that is the term number 2. You subtract 1 from 2, you get 1. That is why we are adding only 1 common difference to the first term. When we move to the third term, we are in the term number 3. 3 minus 1 will give 2. That is why we have to add 2 common differences to the first term. That is why we have to add 2 common differences to the first term. Also, the fourth term, for the fourth term, the term being sought is the term number 4. You subtract 1 from 4, we add 3 common differences to the first term, and so on. So that is why they said the number of common differences that must be added to the first term in order to get the next term is 1 less than the term being sought. That is, to get T4, you have to subtract 1 from 4, so you have to add 3 common differences to the first term. So following this, the nth term, that is, if you now want to generalize the term of that particular AP, noted as T subscript n, as we have in sequence, is given as T subscript n equals to, you had the first term to n, you had the first term, that is A, plus the term being sought here is n. It must be 1 less than the term being sought, that is, you subtract 1 from the term being sought, which is n. That is why we have n minus 1, and you multiply it with the common difference d. So the nth term of an arithmetic progression is A plus n minus 1 into d. So if you want to check if this is correct, let's check for the second term, that is T2. That is when your n is equals to 2. You substitute n equals to 2 here, which is A plus 2 minus 1. 2 minus 1 is 1. 1 multiplied by d will be d. That is why we have the second term T2 to be equals to A plus d. The sixth term T6 will be equals to A plus 6 minus 1, which is 5d. That is why they said it is noted that the number of common difference that must be added to the first term in order to get the next term is 1 less than the term being sought. So here, A is the first term, that is the first number in that particular progression. D is the common difference. We've been given the formula of the common difference, and n is the number of terms. The nth term of an AP is also called the last term, and it's denoted by L. So Tn, we can also write it as L. They can call it last term, that is the value of the nth term, the last term of that particular progression. That means that particular progression is finite. So now we'll move to examples. We solve examples. We solve 5 examples. 3 are from the past UTME questions. Second question is UTME 1989. The third question is from UTME 2001. And the fifth question is from UTME 1994. So now we'll move to the solutions of this example. The first example says the 16th term of an AP is 93. That is, T16 is 93. The value of the 16th term of an arithmetic progression is 93, and the common difference is given as 6. So we are asked to find the first term A and the 28th term. So now we'll first write down the formula for the nth term. Tn equals to A plus n minus 1 into D. And from the question, n is 16 because we are dealing with the 16th term. From the question, n equals 16, and the value for T16, that is the 16th term, is 93. We don't know the first term, and the common difference is given as A. So substitute all these parameters into the formula for the nth term, which is T16 equals to A plus n is 16 minus 1 multiplied by D. And the value for T16 is 93 equals to A plus 16 minus 1 is 15, and the value for D is 6. 93 equals A plus 15 multiplied by 6 is 90. So here we collect the like terms. 90 will go to this side. It's going to change to minus 90. A will be 93 minus 90. Therefore, A is 3. Therefore, the first term of that particular arithmetic progression that has its 16th term to be 93 and common difference as 6 is 3. So now we already find the value for the first term. We will now have to find the value for the 28th term. So to find the 28th term, we know that n equals 28. T28 will now be equals to A plus 28. You know, from the formula of the nth term, A plus n minus 1 into D. So T28 will be A plus 28 minus 1 multiplied by D. Here n is 28, A is 3, and D is 6. T28 will be equals to 3 plus 28 minus 1 multiplied by the value of D, which is 6. 3 plus 28 minus 1 is 27. 27 multiplied by 6 will give 162, plus 3 will give 165. So the 28th term of the arithmetic progression that has its 16th term to be 93, its common difference to be 6, and first term to be 3 is 165. So now we'll move to the second example. It says if minus 8, m, n, 19 is an arithmetic progression, find m, n. This is a UTME past question. It is obtained from UTME 1989. So here, if we look at the arithmetic progression, we will see that it is a finite arithmetic progression with T4 as the last term and 4 as its upper value. So here we know the value for T4 is 19, and the first term, that is the first number in that particular arithmetic progression, is minus 8. Here, we first write down the formula for the nth term of an arithmetic progression, and we know that the first term, which is A, is minus 8, and the fourth term, represented as T4, the value for the fourth term is 19. So now we find the formula for the fourth term from the formula of the nth term. We substitute n to be equals to 4. So T4 will be A plus 4 minus 1 into D. T4 equals to A plus 3D. The value for T4 is 19 equals to value for A is minus 8 plus 3D. So we'll collect the like terms, bring minus 8 to this side, it changes to plus 8. 19 plus 8 will give 27 equals 3D. So to make D the formula, we divide through by 3. So D will be equals to 9. Therefore, D, which is the common difference, is 9. Now we have the value for the common difference, and we all know that M is the second term and N is the third term. So to obtain M and N from the generalized form of an arithmetic progression, we know that the second term, which is M here, is equals to the first term plus D, which is equals to A plus D. That is, to get the second term, you have to add the common difference to the first term to give the second term. Here it is denoted as M, and to get the third term, it is in two ways. It's either you add two common differences to the first term, or you add a common difference to the second term. So here we choose adding a common difference to the second term, and you now know that the value for the second term here is M. It is denoted as M. That is, M plus the common difference will give the third term, which is denoted as N. So that is, you already know the value for the first term, which is minus 8, and the value for the common difference, which is 9. So to get the value for M, we we add 9 to minus 8. Minus 8 plus 9 will give 1. That is the value for m. And to get the value for n, we add m to the common difference, which is 1 plus 9 to give 10. That is the value for n. Therefore, m comma n is 1 comma 10. And that particular progression will be minus 8, comma 1 comma 10 comma 19. Now we move to the third example. This is also a UTME past question, UTME 2001. It says the sixth term of an arithmetic progression is half of its 12th term. Then the first term is, we want to find the relationship with the first term. So here we write down the formula for the nth term of an arithmetic progression, which is t subscript n equals a plus n minus 1 into d. Here we first find the sixth term, which is t6 equals, the value for n here is 6, a plus 6 minus 1 multiplied by d. 6 minus 1 is 5, so t6 equals to a plus 5d. And we also talk about the 12th term in the question. So we now look for the value of the 12th term. The first term is t12 equals a plus 12 minus 1 into d, which is a plus 11d. And from the question they said the sixth term of that particular arithmetic progression is half of its 12th term. So that means sixth term, which is a plus 5d, equals to the 12th term divided by 2, which is a plus 11d divided by 2. So we cross multiply. 2 will multiply a plus 5d and 1 will multiply a plus 11d. So 2 multiplied by a will give 2a, plus 2 multiplied by positive 5d will give positive 10d, which is equals to a plus 11d. So we collect the like terms. A will come to this side because it's the same, and plus 10d will come to this side. If a comes to this side, we have negative a, that is 2a minus a, and here we have 11d minus 10d. 2a minus a is a, and 11d minus 10d is d. Therefore, an arithmetic progression that has its sixth term equals to half of its 12th term will have its first term equal to the common difference. That is, the first term of that particular arithmetic progression will be equal to its common difference. So that answers the question. Now we move to the fourth question. The sixth and 13th term of an arithmetic progression are 0 and 14 respectively. Find the arithmetic progression. Here, the value for the sixth term is 0 and the value for the 13th term is 14. So we have to find that particular AP. We find its first term, its second term, its third term, its fourth term, and so on. So to find this, we have to know the first term and the common difference. So we first obtain the value for the first term and common difference. And from the question, we are given that the value of the sixth term is 0. So we'll use the formula for the nth term of an arithmetic progression, which is Tn equals a plus n minus 1 into d. T6, that is when we are dealing with the sixth term, the value for n will be equals to 6. T6 equals to a plus 6 minus 1 into d from this formula, which is a plus 5d. And since the value of T6 has been given to be 0, we have 0 equals to a plus 5d, and that is tagged as the first equation. And from the question also, the 13th term of an AP, the value for the 13th term is given as 14, and T13 will be a plus 13 minus 1 into d from the formula of the nth term of an arithmetic progression, which is a plus 12d. Since the value of the 13th term is given as 14, it implies that 14 equals to a plus 12d, and it is tagged as second equation. So equation 1 and 2 leads to a simultaneous equation. So now, we eliminate a to obtain the value of the common difference. So we subtract 1 from 2, we have 14, that is, we subtract 1 from 2, 14 minus 0 will be 14, a minus a will give 0, 12d minus 5d will give 7d. So here we make d the solution of formula, so we divide through by 7, and we have d to be equals to 2. So now we have the value for d. We will use this value for d. We substitute into any of these equations, that is either equation 1 or 2, to get the value for the first term a. So here we choose to substitute the value of d equals 2 into the first equation, and the statement for the first equation is 0 equals to a plus 5d, which is 0 equals to a plus 5 multiplied by 2, which is, here we first make a sort of formula. We take 5d to this side, we have a equals to, if 5d crosses to this side, it will change to minus 5d. So A will be 0 minus 5. The value for D is 2. 5 multiplied by 2 is 10. 0 minus 10 will give minus 10. Therefore, the first term of an AP that has its 6 term to be 0 and 13 term to be 14 is minus 10, and the common difference is 2. So we use these two parameters to obtain the terms of that particular AP. From the generalized AP, generalized AP we discussed the other time is of the form A, A plus D. This is the first term. The second term, the third term is A plus 2D. The first term is A plus 3D. The fifth term is A plus 4D. The sixth term is A plus 5D. The seventh term is A plus 6D. The eighth term is A plus 7D, and so on. So now we substitute the values of A and D to get the terms of that particular arithmetic progression. The first term, which is A, is minus 10. The second term is minus 10 plus 2. The value for the first term is A minus 10 plus the value of D. The third term is minus 10, value for A plus 2 multiplied by the common difference 2. And same thing is applicable to all other terms. So now we evaluate this. The first term is minus 10. Minus 10 plus 2 will give minus 8. Minus 10 plus 2 multiplied by 2 is 4, which is minus 10 plus 4 will give minus 6. Minus 10 plus 3 multiplied by 2, which is minus 10 plus 6 will give minus 4. Minus 10 plus 4 multiplied by 2 will be minus 10 plus 8 will give minus 2. Minus 10 plus 5 multiplied by 2 is minus 10 plus 10, which is 0, and so on. So that particular AP is minus 10, minus 8, minus 6, minus 4, minus 2, 0, 2, 4, and so on. So to check if this particular result is correct, we know here that the first term is minus 10. So let's check if the common difference will be 2. So to check the common difference is either you subtract the first term, from the second term, or the second term from the third, or the third from the fourth. So here let's start by subtracting the first from the second. That is minus 8 minus 10. Minus multiplied by minus will give plus. So minus 8 plus 10 will give 2. Also, minus 6 minus 8 is minus 6. Minus multiplied by minus is plus. Minus 6 plus 8 will give 2. Therefore, this is a particular arithmetic progression that has its 6th term to be 0 and 13th term to be 14. So now we move to the 5th question, which says if the 6th term of an arithmetic progression is 11 and the first term is 1, find the common difference. The value for the 6th term is already given as 11 and the value for the first term is 1, so we are asked to find D. So from the formula of the nth term of an arithmetic progression, Tn equals A plus n minus 1 into D. From the question, n equals 6. The value for the 6th term is 11. The value for the first term, A, is 1. So we have to obtain the value for the common difference. So substituting these parameters into the formula of the nth term, we have T6 equals A plus 6 minus 1 into D. The value for T6 is 11 equals the value for the first term is 1. 6 minus 1 is 5. 5 multiplied by D will give 5D. So collect the like terms. We move 1 to this side. We have 11 minus 1 equals 5D. 11 minus 1 is 10 equals 5D. So to make this a formula, we divide through by 5. And so if we divide through by 5, we have D to be equals to 2. Therefore, the common difference of that particular arithmetic progression that has a 6th term to be 11 and the first term to be 1 is 2. These are exercises to solve to check if you really understood what we have been explaining. Now move to the properties of arithmetic progression. The first property: if a constant quantity is added to or subtracted from the terms of an arithmetic progression, the resulting sequence is also an arithmetic progression with the same common difference. So we move to the proof of this particular arithmetic progression. We all know that the first term of an arithmetic progression is A and D is the common difference. Then the general term of that arithmetic progression is A, which is the first term, comma a plus d the second term, comma a plus 2d the third term, up to the n minus 1 term, which is a plus n minus 2 into d, and the nth term a plus n minus 1 into d, and that is tagged as the first equation. So here the proof is divided into two parts. The first part is the addition of constant quantity, and the second part is the subtraction of constant quantity from the terms of an arithmetic progression. Now we move to the first part, addition of constant quantity. If a constant quantity k is added to each term of 1, which is the generalized term of an arithmetic progression, the resulting sequence will be a plus k, a plus d plus k, a plus 2d plus k, up to a plus n minus 2d plus k, a plus n minus 1d plus k, which is started as second equation. The first term of this new sequence, that is the first term of 2, is a plus k. So to check if this new sequence is an arithmetic progression, we check if it has a common difference, a unique difference. That is, if we subtract the first term from the second term, the result must be equal to subtracting the second term from the third, which must be equal to subtracting the n minus 1 term from the nth term. So let's start from subtracting the first term from second term. A plus d plus k minus a plus k will give d. Also, a plus 2d plus k minus a plus d plus k will also give d. And also, a plus n minus 1d plus k minus a plus n minus 2d plus k will give d. So since it has a unique difference, therefore the terms of the above sequence 2, that is the sequence you generate when you add a constant quantity to each term of an arithmetic progression, it also forms an arithmetic progression. Hence, if a constant quantity is added to each term of arithmetic progression, the resulting terms are also in arithmetic progression with the same common difference. So now let's move to the second part of the proof, that is the subtraction of constant quantity. If a constant quantity k is subtracted from each term of 1, that is the generalized form of an arithmetic progression, the resulting sequence will be a minus k, a plus d minus k, a plus 2d minus k, up to a plus n minus 2d minus k, up to a plus n minus 1d minus k, and that is tagged as the third equation. The first term of the third equation, which is the sequence obtained by subtracting the constant quantity from the terms of an arithmetic progression, is a minus k. To check if this sequence also forms an arithmetic progression, we check if it has a unique common difference. So to check, we subtract the first term from the second, which is equal to subtracting the third term from the second term from the third, which is also equal to subtracting the n minus 1 term from the nth term. So to check this, we subtract the first from the second, a plus d minus k minus a minus k, we give d. Also, a plus 2d minus k minus a plus d minus k, we also give d. And also, a plus n minus 1d minus k, we give a plus minus a plus n minus 2d minus k, we also give d. Since we have a unique difference, therefore the terms of the above sequence 3, that is the term generated when you subtract a constant quantity from the terms of an arithmetic progression, also form an arithmetic progression with common difference d. Hence, if a constant quantity is subtracted from each term of an arithmetic progression, the resulting terms are also in arithmetic progression with the same common difference. So this completes the first proof, the first property. Here we move to the second property. If each term of an arithmetic progression is multiplied or divided by a non-zero constant quantity, then the resulting sequence forms an arithmetic progression. That is, if you divide each term of an arithmetic progression or you multiply them by a non-zero constant quantity, that is a quantity that is not equal to 0, then the resulting sequence also forms an arithmetic progression with a unique common difference. So this proof is also divided into two parts. So we start the proof by assuming that the first term of an arithmetic progression is denoted by a and d is the common difference, and the general form of an arithmetic progression is given by equation 4. So the first part is the multiplication of a non-zero constant quantity with terms of an arithmetic progression. So if a non-zero constant quantity k is multiplied by each term of 4, the resulting sequence will be ak plus dk, ak plus 2dk, up to ak plus n minus 2dk, comma ak plus n minus 1 dk. So here we know the first term of this new sequence 5, which is generated from multiplying a non-zero constant quantity k with the terms of an arithmetic progression has its first term to be ak. So to check if it also form an arithmetic progression, we check if it has a unique common difference. That is, if we subtract the first term from the second term, it will be equal to subtracting the second from the third, and also equals to subtracting the n minus 1 term from the nth term. So ak plus dk minus ak will give dk. Ak plus 2dk minus ak plus dk will also give dk. Also, ak plus n minus 1 dk minus ak plus n minus 2 dk will also give dk. Since we have a unique common difference, therefore the terms of the above sequence 5, this sequence, form an arithmetic progression. Hence, if a non-zero constant quantity is multiplied by each term of arithmetic progression, the resulting terms are also in arithmetic progression. So we'll move to the second part of the proof, that is dividing the terms of an arithmetic progression by a non-zero constant quantity. Also, if a non-zero constant quantity k divides each term of 4, that is the generalized term of an arithmetic progression, the resulting sequence will be a over k, comma a over k plus d over k, comma a over k plus 2d over k, up to a over k plus n minus 2d over k, comma a over k plus n minus 1d over k, and that is tagged as the sixth equation. The first term of this new sequence is a over k. So we check if it is a common difference, if it is an arithmetic progression, by checking if it has a unique common difference. So we check by subtracting the first from the second. If you subtract the first term from the second, we have d over k. If you subtract the second term from the third, we also have d over k. And also, if you subtract the n minus 1 term from the nth term, we have d over k. Since it has a unique common difference, therefore the sequence 6 above form an arithmetic progression. Hence, if a non-zero constant quantity divides each term of an arithmetic progression, the resulting terms are also in arithmetic progression. And that completes the proof of the second property. Now we'll move to the third property. In an arithmetic progression of finite number, that is, it will be a finite arithmetic progression to have finite number of terms. We have an upper value and an end and a last term. The sum of any two terms equidistant from the first and the last term is equal to the sum of the first and last term. That is, if you have a term that has the same distance from the first and the last term, if you take the sum of its term from the last, if you take the sum of that particular term from the last term and that particular term from the first term, if you take their sum, it is also equals to adding the first and the last term. So suppose A is the first term, D is the common difference, L the last term, and N is the number of terms of an arithmetic progression. The second to the last term, that is the term before the last term, you have to subtract the common difference from the last term to get the preceding term before the last term. The third term from the last, that is the two terms before the last term, you have to subtract two common differences from the last term. The first term from the last, you subtract three common differences from the last term. So therefore, the out term, that particular term we are talking about that has the same distance from the first and the last term, to get the value of that term from the last term, it is like subtracting the r minus 1 multiplied by d minus l. That is, here when we want to get the fourth term from the last, we subtract 1 from 4. That is why we have to subtract 3 common differences from the last term. The third term, 3 minus 1, we subtract 2 common differences from the last term. So the r term is r minus 1 differences from the last term. So now we have already gotten how to get the value of the r term from the last term. So now we have to get the value of the r term from the first term. That is, from the idea of nth term of an AP, the r term from the beginning, that is, the r term of an arithmetic progression, since we have the nth term to be a plus n minus 1 into d, so the r term will be a plus r minus 1 into d. So therefore, the sum of the r term from the beginning, that is from the first term, and the last term will now be a plus r minus 1 into d, plus, since we are adding, l minus r minus 1 into d. So this, we cancel this, so we have a plus l, which is the first term plus the last term. And this completes the proof. Hence, The sum of two terms equidistant from the first and last term is always equal to the sum of the first and last term. And those are the properties of an arithmetic progression. Next video will be on geometric progression and its properties with sample questions and solution. Please subscribe to our channel, our YouTube channel, like and share our videos. Thank you.